and some properties of atoms and ions, and how they interact with each other, so what makes like covalent bond to covalent bond and all that sort of thing. Before we can really understand those principles, we need to have a pretty good understanding of the particles that make up those things, so the atoms, and therefore their subatomic particles, the things that make atoms up. We're not going to go deeper than the subatomic particles that we met in years 9 through to 11. We're going to stay just with the simple ones. We're not going to go down to quarks and all that sort of thing. We're not even going to get hung up on the wave-particle duality of electrons. All right, what we're going to think of is that they're particles that have a charge which can be attracted or repelled by other particles. So what I'm going to ask for quickly is a reminder on how an atom is arranged, and we can use our old Bohr model if we want to. What do we find in the middle? What's in the middle of an atom? The nucleus. Okay, so we've got this thing in the middle that we can call the nucleus. We're not going to do it to scale, but in here we've got our nucleus. Okay, what particles will we find in this nucleus? Neutrons. Okay, I'm just going to show one, and I'm going to put a little zero next to it. Can anyone guess why I put a little zero? Has no charge. Okay, so I'm doing basically as if it was a chemical reaction. I'd write N with a zero because it's got no charge, doesn't affect it. What else do I find in the nucleus? Protons, which is P positive. So they have a positive charge. What we're worried about, what we're about to do, are the protons, not the neutrons. Okay, the neutrons, so isotopes and that sort of thing, are not important. What's important is the number of protons. How do I determine the number of protons in an atom or an ion, a monatomic ion, one atom ion? How do I determine the number of protons?
Is it the atomic number?
Atomic number, great. So I do have information to help me with that. No, let's use that one. It's the atomic number, which is the smaller number for those symbols on the periodic table. So for lithium it's 3, which means it has 3 protons. We can ignore the number of neutrons, okay? Isotopes are important in our last unit, not this one. Neutrons plus protons are the mass number, okay? As I say, not important. Now in an atom, the atomic number is also equal to its what? Its number of protons and the number of electrons. Awesome. How are electrons arranged around an atom? How are they arranged? You can go as far as you like with your answer here.
Like shells?
Shells, which we're calling energy levels now. So again, not to scale and only showing a bit of it, we've got shells or energy levels or quanta number where we're going to find electrons arranged. Where do we start filling up these energy levels or shells or quantum numbers or whatever?
And the energy level closest to the nucleus.
Cool. So we fill this one up first, which is the first energy level, or N equals 1. And so we start filling up with how many electrons?
2.
Only 2. We can only take 2. All right? So we can get up to 2. Then there's the second energy level, third, fourth, and so on. Okay. The second energy level is another one of the smaller ones. Because it's so close to the nucleus, there's not enough space for lots of types of orbitals, is what we call them. There's only room for the s orbital and the p orbital. So s orbitals can take 2 electrons, p orbitals can take 6. So how many electrons will fit in there? 2 and 6. 8. So we can get up to 8 electrons there. So once we've filled this, we start filling this, and so on. Just the d orbital comes in here, so this one can take 18, so can the next one, and then things get a bit interesting, which is why I haven't done the 5th. Okay, things start getting a bit, very interesting beyond that. So, now we want to look at the forces of attraction and repulsion. Within the nucleus, it is held together because of the way the protons and neutrons are arranged. We don't need to worry about the nucleus. If something's happened to the nucleus, We'll leave that for the physical for the physicists, the nuclear physicists. Okay, that's the awesome stuff that they look at. What we're looking at is the relationship between electrons and electrons and the protons in the nucleus. We're going to be looking at a thing called effective nuclear charge, which in your work that you're doing there, we're going to look at. You'll see that word being used. Effective nuclear charge. The nuclear charge gets bigger and bigger the more watt in there. If I have more watt in there, what will that... Sorry?
Protons.
Cool. The more protons. How do I know something's got more protons than something else?
About a
Larger atomic number, okay? But that doesn't mean it has a bigger effective nuclear charge. There are other things that affect how strong that is. Affect, but that's okay. So, if I had a look, for example, at the radius of lithium versus sodium, sodium has a larger nuclear charge, but it has a smaller effective nuclear charge on the outermost electron. And the reason is that that outermost electron for sodium is out here, whereas for lithium it's here. What's one thing, and those who do physics might get this, we're talking about electric attraction, what's one thing that would cause, even though there's more protons here, this one to be held less strongly in sodium than this one is in lithium? Distance. Distance is a critical thing for determining effective nuclear charge. Okay? This is going to be very important in a moment. I'll revisit this. The other thing that's important about nuclear charge there is a thing called shielding. These electrons here, if there are electrons in the first energy level and the second, these ones shield the effectiveness of that nuclear charge. They effectively get in the way every now and then of them being able to attract the electrons beyond them. So we call this shielding. So an electron out here is not only miles away, it's also being affected by all of this shielding by electrons at the lower energy levels. So it's called electric shielding. And the really easy one to explain would be, for example, why would these electrons in magnesium be held tighter than these electrons in sodium?
Magnesium has a larger nucleus.
Larger nucleus, so more protons. So actually, if everything is equal, so they're all in their outermost electrons are all in the same energy level, then the most important thing is going to be the nuclear charge itself. So you take the word effective out, it's the nuclear charge, which is due to number of protons. So these are the things that affect how strongly the electrons are held. This will have an impact on radius, how big something is, on the ionization energy, the amount of energy required to remove electrons, because the harder they're held in, the harder it is to rip them off. It will have an effect on electronegativity, because it will affect how well this nucleus can hold on to bonding electrons. And it will have an impact on, the other two main ones we need to worry about, but it will also have some impact if we add or lose electrons to make ions, as to the size of the ion compared to the parent atom. Will it be bigger or smaller, and why? These are not the only things that affect, or these are not the only forces in there. I've put attraction. These are all to do with attraction, except for the electric shielding, which is a shielding, so it's actually kind of stopping it getting through, so it's not attraction. There's also electric repulsion happening. Where would that electric repulsion be occurring? Again, we disregard the nucleus because that's for the physicists to worry about. Between electrons, okay? So, you're going to have electrons in the same energy level. The more you pack in there, the more chance there is they will repel each other. So therefore they need more space. So while these are energy levels, they tell us about the energy of the electrons. They don't tell us how far away from the nucleus they are to be stably there. They can be a bit further away or a bit closer. And the orbitals also can be a bit closer or further away depending on the type of orbital. That's important for distance. Talk about that in a second. Because they may have the same energy, but they may be in different spaces. So they can get a bit closer to the nucleus or have to be a bit further away. Okay? So we get electric repulsion as well. So if you have a full energy level, or nearly full energy level, they start to repel each other within the same orbital. Okay? So we've also got, I might put it here actually. To show the impact of electron-electron repulsion, one of the best things you can do is draw what's called an orbital diagram. And as you work through your work, you'll see what an orbital diagram is, and it shows basically that if you've got some half-filled suborbitals and you've got some filled suborbitals, so some have got one and some have got two of them in it, you'll see that actually they have slightly larger radii than you'd expect because there's a bit more electric repulsion there. It also explains why anions, negative ions, are quite a lot bigger than their parent atom. Because just adding that one more or two more or three more electrons into the valence shell, as it were, that outermost energy level, there's no increase in nuclear charge or effective nuclear charge, but there's more electric repulsion, so it gets a lot bigger. Because you've got more electrons in the same energy level, so they have to get away from each other. Right, I said I'd talk about distance. Just so you're aware, distance within an energy level can be dictated by the orbital that the electrons are found in. The s orbital is a sphere, so there's a lot more space for those electrons to go in, so they use it up. So s orbitals tend to take up a little bit more space than p orbitals of the same energy level. This is really important when you're explaining things like why has beryllium got a, I'm just going to this one here, we're looking at ionization energy. Why does beryllium hold on to its electrons a lot tighter than boron? That goes against the trend we'd expect to see. It's because beryllium's electrons are all in s orbitals, which, you get held a bit tighter, that's right, and then boron's is released a bit. So you've got to have a look at your distance of these orbitals because they're not always the same. Some orbitals are held a bit closer. D are really useful because they tend to sit, if we're looking at it like this, the 3D orbital sits about here somewhere, which means you're going to have that slightly larger radius. Okay, a bit more shielding on these, which will push them a bit further out if they're there. So those are your main forces. You've got the effective nuclear charge, which is hard to work out because you've got to understand about electric shielding. Okay, distance is the easy one, and the number of protons is the easy one there to explain. You also need to look at the electron-electron repulsion. Okay, in other words, how full are those orbitals, so those electrons likely to interfere with each other, so require more space to be stable. Once you have an understanding around those two ideas there, you can start applying it to atomic radius, ionic radius, and therefore understanding electronegativity, trends, and periodic trends. Also understanding about these orbitals here will help you understand why certain elements have unexpected electron configurations, like chromium and copper, and you can use things called Hund's rule and the Aufbau principle to help explain those as well. So all of the work that you've got to do for the next week and a half, basically there's an overview of background that might help you answer that.